Okay, so like Jed said, I'm from PlanetOS, and we do a bunch of work on AWS, focusing on different data stuff. I want to talk about that today. But before I get started, I really want to talk about why the cloud is so good for this kind of application. And what we found at PlanetOS is, and I think a lot of other people are finding this too, is that when you're working in the cloud, you tend to be able to compose parts of systems together and connect systems from various sources, various companies, various institutions, connect data much more easily than we used to be able to when we had our own dedicated data centers. And in particular, I think the rise of the cloud is tightly coupled with the rise of APIs. How many people here know what APIs are? So most of you. So for those who don't, APIs are a way you can talk, the programs can talk to each other. And that's a huge growth area right now. We're part of that at PlanetOS, but we're one of many, many. And so today, this is going to be a little bit of a schizophrenic talk. I'm going to talk about a bunch of stuff PlanetOS does generally with AWS, and then I'm going to dive deep on some of this climate stuff, and we'll actually, as Jed said, do a live demo, the internet fates willing. And then I'm going to talk about a couple of other use cases, and we only have about half an hour, so I'm going to go super fast. Okay, so we've all talked about this problem today. The world is exploding. There are so many different kinds of environmental sensors out there, so many different and all of them are generating more and more data. And so we live in a time that is filled with opportunity because of this, but also filled with challenges just to keep up with the data, to store the data, to use the data, to figure out how to analyze the data. One thing we haven't talked about too much is part of the problem is not just the size of the data, it's the fact that data comes to us in so many different formats. And this is particularly true, the guys who are building e-commerce sites, they don't really have this problem, but those of us who are working in the environment and working with Internet of Things and other parts of the real world, we get data in vector formats and array formats and special raster formats like what Jed was talking about with Landsat this morning. And each of these formats is different. We have to worry about geography for most of these things, and each of them thinks about geography differently. So there's a cross-registration problem that's immense. And so as we begin to write applications to try and use this data, we find ourselves, Jed talked about an 80% number of processing data. I think with data that's geospatially aware, we spend more than 80% of our time dealing with figuring out how to just absorb the data into our applications, to build applications. So PlanetOS exists partially to ameliorate this by creating common interfaces and doing pre-processing. So in agriculture, we also have another issue going on with the fact that we're now getting a lot of data about our fields and about how things are working on farms. People are putting sensors on tractors and sensors embedded in fields. At the same time, of course, we all know the weather's just getting crazier and crazier, so we have issues. We have the issue in California, of course, that you guys are spared from, but we're living in an age of droughts now. So PlanetOS wants to not only, our products not only deal with this new world of IoT, but we also integrate it with a lot of environmental data that's out there, commercial data and public data, and of course that's how we ended up working with Jed and company. So we talk about making data flow from all these sources, IoT, but also forecasting and satellites and other places into a common API where people can use it for agriculture and for other things. So now I want to dive into a use case example. This is a use case example based on the work that Jed's team has done at AWS and that the NASA Earth Exploration team has done on OpenNex, which puts a bunch of data sets freely available in S3. It's an awesome project. The only problem is big chunks of data are hard to deal with even if they're publicly accessible. And so we came in and looked at this with our technology background and began to think about how we wanted to make those data sets easier to approach. And so we built a tool, and people shouldn't let me name things because I named it. We call it the Climate Data Access Tool, and this is why I'm not in marketing. But in any case, it is an access tool for two of the data sets in OpenNext, and we'll walk through those. But they're both climate data sets, and they're both based on the CMIP5 Common Modeling Initiative for Climate things, and we'll look at that in a sec. The idea behind this is we have a website that lets us interactively choose data from this modeling environment. We'll actually dive into the website in a minute, so I won't belabor this. And then lets you access the data in whatever tool you like to use for using data. So these examples, actually the one on the left is in RStudio, and the one on the right is in Python Jupyter, which are my two favorite tools. But other tools work too. So that's all pretty cool, but I like to actually not show PowerPoint slides all day. So let's have some demo. If I can actually operate Jed's computer. Okay, so, oops. Okay. Jed's going to work his own computer for a sec. Can we just mirror? So I can see what I'm doing?
Obviously, yeah.
I need to be able to
That's not a good, that's not a good idea.
I can't do a live demo and not actually see the type.
Beautiful. Can you see that? It's pretty.
Well, I'll make it bigger.
Okay.
That's okay. Okay. I expect you all to be able to read all of this. Now let's. Okay. So, okay, what I want to do now is get some data from that website. So let's go look at the website right now. The website's called opennext.planetos.com, and you can go there too. It's free and it's usable by everybody. And it looks just like it did on the slide. So this is what it looks like coming up. I'm going to see, I have a stored thing. I'm going to see if I can pull up here that I bookmarked earlier. So let's see if we can. Let's see if I know how to do this. I'm not sure I do. Okay, I'm gonna pretend to do this. I'm on Jed's computer and I don't have the right shapefile here, but you'll see how it works, and then I'll actually use an old version of it because I built it off a. Well, actually, we can use this one. Okay, so this is the interface. We can select what we want right on this interface. And the first thing to know about the OpenNext climate models is they have climate models that were developed by institutions all over the world. They were run against a set of common assumptions about carbon emissions at the NASA Supercomputer Center at Ames. And the model data is there from the year 1950. They ran the runs retrospectively as well as prospectively through 2100. And the two different data sets are different granularity and different time steps. The one I'm looking at here is for the continental United States, and it's monthly data across 3 variables at very fine resolution, about 800-meter resolution. So we can actually look at what the models tell us going forward. I'm going to pick a NOAA model that I like, but as you can't really see this here. But they're models from Europe, China, a bunch of U.S. government agencies, Japan, just different institutions all over the world that are doing climate modeling. And this is pretty straightforward. I can do I'm just going to take, usually you're doing longer baselines than this. Climate data isn't that useful in short things, but for demo, I sometimes do short things. So I'm just picking, can everyone see what I'm doing here? Okay, good. And I can pick, for example, precipitation, and these are the different scenarios. These are standardly defined carbon emissions and land use scenarios that have been developed in the climate modeling community to sort of serve as proxies for combinations of policies around emissions. For next year, it doesn't really matter. No policy changes are going to make any difference that close. And normally what I would do here is I would pull a file from my GIS system. But I'm on Jed's computer. I don't have any files from my GIS system. So what we can do instead is just draw a polygon. And I'm going to try and draw the approximate polygon that I was going to use for the demo. Actually, why don't we just do Columbus? My original one was a more agricultural area, but. Okay, so now we have an area selected, we have the scenario selected. So now we've decided what data we're interested in. We're interested in a year's worth of precipitation data for next year for the area around Columbus. And we've selected that data. And the nice thing about this is we didn't have to do any programming or anything else. Now I'm not going to actually get that data. What I'm going to get is a marker for that data. And of course, I picked the wrong scenario. That model doesn't have an RCP 6.0 scenario. So now I got a new marker for that scenario. We called a permanent link. The nice thing about this marker is now that I've chosen this data, I can share both this web page and the data that I've selected with the web page just by giving someone that permalink. So if I do some research around a particular data set and I use that model, I can now go to Jed or to whoever else wants to work with the data and say, here's the data I worked with. I don't have to send them a data set. I don't have to show them the provenance or anything else. They can just go to this website. They can look at it. They can run the exact same different research on it. This is really important in an age where we're having trouble reproducing results. Okay. So let's actually get this data and use it. Now what I've done, I'll explain this in a sec, but I've set up a back-end server that will process any one of these things in EC2. And so now I can just give that server this number, and we can look at what these precipitation looks like. I'm using RStudio here. How many people know what RStudio is, or are? Okay, about half of you. It's a statistical. It's a language for doing statistics and modeling that I use for most of my analytics work. You can also use Python, MATLAB, ArcGIS, whatever you want to load your data into. What you can see here is, I'm going to go over here, which is going to mess up the recording, but what you can see here is what I'm basically doing to load this is calling read CSV. This is one of the things we do here is we normalize the data, in this case to a CSV format, but you can choose other formats if you want to work with other formats. So do people know what CSV is? Okay, good. And so this is a great way to get data the way you want to use it, and then you can just use that data. So let's do that. So I'm just going to call that function with the magic link that I got, and it's going to read the CSV for that link. Oops. Sorry, wrong button. So now this will take about a minute to load. As we do that, what we're going to do here is look down and put that data on a map. Oh, it didn't even take that long. It was fast today. So we can see we got 86,000 rows of data. This is actually the advantage of running this in EC2 near the data that Jed was talking about earlier. It actually processed, I don't know, maybe half a gigabyte of data to get that, but it pulled it from S3 in EC2 and then just gave us those lines. Again, this notebook is running as a server on EC2, so it didn't have to move the data after that, and all it had to do was display the digits. Oh, I cheated a little bit when I said all we had to do was read the CSV. In fact, there's another very important part to this, which is that we needed to convert the rainfall from the metric units that NASA likes, which is kilograms per square meter per second, which is not a unit that makes any sense at all to me, into inches of accumulation. So we ran that function, and we see here we have precipitation, which ranges in Columbus from 0 to 8 inches. So let's actually look at that on a map. We have some functions in R for just laying this data out on maps, and that's pretty easy to do. And then I want to look at it for each month, so I actually built that in. And now we see it loading map tiles for this. Okay, so now we can see that polygon I drew. We see the different precipitations and this is based on climate modeling. It's not actually a real forecast, but what it looks like in different months. Now, one of the things about doing this in Ohio is that there's actually not a lot of variation across any any polygonal region because Ohio is pretty flat. When we do this in California, we see actually massive variations depending on where the mountains are. Even in parts of California where you don't think they're mountains. But what we see is May is kind of the big precipitation month here, and you can see the ranges for different months. It looks like the region is very uniform in May, or in May. It's all dense. Part of that's because the variation is captured over the whole year, but let's look at what the variation is just for May. And that's easy. I just subset it by 1 month. And now you see there is actually some variation in what the predictions predict, but it's less than an inch of variation over the month. This is actually more than most places in Ohio, except maybe up by the lake. Okay, so that's our demo, and I can tell you guys more about that later. One of the things that's interesting about this, let's get back to here. Okay. Actually, hang on. Oh. Okay, Jed, will you give me a warning when there's 5 minutes left? Because I don't have my timer anymore. Okay, one of the interesting things that's interesting here is what we've done is we've created a component that does the transformation for you. So rather than having a web service that does everyone's transformations, we make this completely self-serve. What we did on the website was just make a selection of data. That selection can be used by this transformation component, and it's deployed with a tool called Docker, which some of you have probably heard of. But what that means is I can deploy it in EC2 like it was deployed here, or I can deploy it on my laptop, which I do a lot when I'm not at a conference and I'm worried about the network connectivity. And I'll get slower performance, but I can use it more flexibly. The other thing I can do is I can use it in combination with other web services. So what you were just looking at is I have a version of RStudio running actually on the same EC2 node that the transformation is running on. I can do similar things with Python and Jupyter notebooks. And so that means I can do things like create classrooms or laboratories for students, all of whom can use the same data sets and the same data environment without having to set it up, but they just go to a website and they can manipulate the data using high-level statistical and modeling tools with the maps and everything else that we saw. So that's a pretty powerful way to work, and that's what you see here. And this is all coming off the same data in the back. It's straight S3 data, and this whole project is freely available. So if you go to opennext.planetos.com, you can just use it. Okay, so I'm going to talk a little bit about how we model the world. We look at data in the world coming from various sources. I just showed you one, which is the sort of a custom-built app for that. But in general, we're acquiring data from all sorts of sources and storing it. We take advantage of both S3 and Amazon's various other storage options to keep data and to keep data about data. So that we can index it very quickly and deliver it to people. And then we use EC2 for doing all the execution of how to grind up the data and index it and then deliver it via APIs. So we can work both with operations as well as with data scientists doing exploration. What I showed you was more of a data scientist use case, but we also work in a variety of cases with, for example, dashboards, where we build the dashboard for RWE, which operates various large offshore wind farms. So that's OpenNext. One of our examples, and I'm going to dive into this example a little bit more here at the end, is a company called The Yield. This is we'll talk about that in a sec, but and Gaia. These are both ag companies, not based in the U.S., but that are doing very data-driven agriculture that are using our system. So we have three parts to our system. One part is the engine. This is the part that goes and crawls data sources, whether they already live in AWS or whether we're pulling them into AWS to analyze them, and analyzes data as it comes in. So for example, for a data source like the global forecasting system that NOAA produces, we index that data every few minutes to get the most up-to-date data so that we can deliver global forecast data that correlates with other kinds of sensor data for whatever geographic region you're interested in. Then we have Data Hub. Data Hub is a combination of a data selection interface, but most importantly, it provides an API to all this data. And it lets you do APIs in JSON format, CSV format, or in NetCDF OpenDAP format right now. And we're adding new formats so that users can get data in the format they're interested in, regardless of the formats that are out there. And then the final part of this puzzle is PowerBoard. PowerBoard is our toolkit for building custom data integration applications. And it's, for example, used by RWE for the Gwynty Moor wind farm, which is the second largest offshore wind farm in the world off Wales, and is being deployed throughout RWE now. So we also we talk about Enterprise Data Hub. That's for enterprises that want to publish their own data. The OpenNext project kind of started as that, but has now become more of a public project. So Data Hub itself is a repository of all sorts of mostly open data sets, but we have commercial data sets as well. 49, this slide tells me. It might even be higher now, but we add new ones every week. They're mostly targeted on three areas: renewables, in particular. We talk about power generation, but all our work is in renewables, wind and solar, and agriculture and energy trading. So here's the example case I was talking about, The Yield, a company that works with farmers in Australia and Tasmania, and they're using our system with a bunch of different variables to augment what they're doing with IoT in the fields. This includes, so here's some of the data sets they're using: volumetric soil moisture, precipitation, cloud cover, temperature, runoff. And so the interesting thing here is, how does it, where do we fit, right? So if you're going to use tools that PlanetOS produces, where would you use them? And of course, there's all sorts of things that go into a data analytics app. It's not our goal to do all of these, but instead, we're focusing on three specific areas. Oops. Three specific areas. The engine focuses on this getting data and storing it and having it in one place. And again, we're leveraging Amazon storage options to do this. We're also a little lazy about storing things. Sometimes we don't pull things that people aren't using. And then Data Hub provides a set of APIs, selection and APIs around that, so that you can integrate. One of the great things about using Data Hub is you get this API that gets you just the data you care about, and you don't have to worry about processing the data sets. You saw how I did that with OpenNext. Data Hub provides that for all 49 data sets, and so you can just pick what you're interested in and pick the restriction region and just pull in the data you care about. And then PowerBoard works on the other side, data viz and dashboarding for real institutions. And with PowerBoard, we're mixing data from both proprietary sources typically. Sometimes that's SCADA sources on machinery. It could be sensors and fields with public data like forecasting, and even, well, offshore we do a lot of stuff with shipping data and so on. So we know where the boats are. And that's what I got. So I know that was a little bit of a fire hose, but if anyone has any questions, I'm happy to talk about what we've done or what we have or anything else. I run right up against the edge, yeah. Sorry, I didn't have I lost the timer in the middle there when we were changing screens. Sure. It's not up now, but it's easy to publish. We do have a couple of things. I did a blog post, actually on my personal blog, about the Tuolumne watershed, which is where San Francisco gets its water from Hetch Hetchy Reservoir in the Sierras. And so it's particularly interesting to me, with all the code included. And I think we have another notebook up, but I can share this stuff too. This is, it's all out of my sort of personal hacking bin. Right. So to talk about SQL specifically, SQL is typically not a very good API for dealing with large swaths of environmental or sensor data. A better interface language is something called something like NetCDF, which is actually thinking in terms of arrays, and we do provide OpenDAP support, which is the interface for NetCDF for all of our data sets. For some users, the data that they get back from that is more complex than what they want. They want simpler data. And for those cases, we provide, simple data. It's like, I want the temperature and wind for my town so I can put it in an iPhone app, for instance. We talk about very sophisticated use cases, but there are a lot of simple ones like that people want. And we provide the simpler interfaces for that. Okay, so yeah, I'll be around for the next couple of hours until I have to run and catch my plane. Grab me, and I'm happy to talk about any of this.